Hey there, 205. I hope you're doing well. Today, we are going to do something totally new. We are done with the research design aspect of the course, and now we're going to start talking about analyzing data. Now, there is a lot in this section that I am getting rid of because we're doing this online. You guys don't have access to the computer programs that you would normally need to run these things on your own. So I'm sort of rearranging how to do this to make things easier on everyone. So this is where we are in the overview of the course. We're kind of skipping over the collecting data phase because you guys aren't actually collecting data. You're just sort of proposing how you would collect data. And we're going to talk about what it means to actually look at data and analyze it and interpret the results of a study. So this is how I have this outlined right now. We will talk about data collection and looking at it, and we will talk about correlations between variables. And then we'll spend a decent amount of time talking about something called linear regression and how that works sort of in the computer behind the scenes. We'll spend a big chunk of time talking about how to run a bivariate linear regression with all of the different things you have to interpret. And then we will add control variables to that regression. So that's what we're going to be doing for the next 2 weeks. You do have to watch all of these videos in order to do your regression homework. But this video is just going to focus on some basic stuff, what it means to look at data and run a correlation between variables. Okay. So when we collect data, if you were to use a survey or a poll or some sort of study that's done on a computer, that will generate a data file for you, and all of the variables and all of the data will end up in the same spreadsheet. That makes life really, really easy because remember, when we analyze data, it needs to all be in a spreadsheet for us to actually analyze it. So if you do a poll or a survey, that makes things quite easy. But anything else that you do, if you're collecting data from the crime stats or economic data for countries around the world, you have to put all of that data into a spreadsheet. So that's a little bit more work, but that's on you. You have to combine those things. So I've come up with some example of what a spreadsheet of data would look like. So we're going to walk through each sort of piece of the picture here so you guys can know what this actually looks like before we analyze it. So here is an example spreadsheet, and let's say that I'm interested in members of Congress and whether they take super PAC money. That's my dependent variable. What affects if they take super PAC money, maybe their ideology? I don't know, I'm just making this up. So let's go through the parts of this spreadsheet. In yellow right here, we have something called a connecting column. This basically means these are your units that you're analyzing. In my fake study, my units are each person in Congress. So it's individuals in Congress. Bob Johnson, Janice Fuller, Maria Hernandez, these are made up names. But each of them has their own sort of row in the data sheet, which means that they're all in the same column. So that's our connecting column, or that's each unit that we are analyzing. This in yellow is called a case. Bob Johnson, who is one of my individual units of analysis, he has his own row. So that means everything in that row relates to Bob Johnson. So does he take super PAC money? He has a 1, which in my data set means yes, he does. A 0 would mean nothing. So Bob Johnson, he gets a 1 for taking super PAC money. What is his ideology score from, 0 is really, really liberal to 1 is really conservative? He gets a 0.87, so that's his ideology score. What percent of his district has black residents? 12%. What percent of his district is unemployed? 6%. So everything in that row relates to Bob Johnson, and that row is called a case. On the left, everyone has a case ID number that is unique to them. We won't really get into this, but every single data set has a number that's associated with each unit that is completely unique. These are all of the data for our variables in yellow. So whether they take Super PAC money or not, that's all in this column. Their ideology scores, all in this column. So these are all my variables, and the numbers vary because they are variables. And the entire thing is called a data matrix. So that's what looking at your data would look like, but you guys know that in quantitative political science, we wouldn't have just 6 units of analysis, we'd have hundreds and hundreds. Okay, so now let's talk about actually doing a little bit of analysis, and we're gonna start really basic. What is the relationship between X, your independent variable, and Y, your dependent variable? How does one affect the other? Or maybe it doesn't, we don't know yet. So the most basic stuff that we're looking for here, there's really 3 things. We're looking for the direction of the relationship, which we've talked about earlier in the course. Is it a positive relationship? Is it an inverse relationship? Or is there no relationship? So positive, as you know, means X goes up, Y goes up, or X goes down, Y goes down. So what's the direction of this relationship? What is the strength of the relationship? So how much does X predict Y? Does it predict it a lot? Is there a big impact of X on Y, or is there a small impact of X on Y? And then finally, the significance of the relationship. And we'll talk about this extensively in another video. This is whether this relationship happened due to random chance or not. There's always a possibility that X doesn't actually affect Y, that just happened randomly. So those are the 3 basic things that we're looking for when we're trying to understand relationships between variables. So let's start with the most basic thing that we can do. This is going to help us examine the direction of the relationship, and it'll give us some indication of the strength. And that's called running a correlation. You guys have probably heard this word before. A correlation is a statistical measure that indicates the extent to which 2 or more variables fluctuate together, right? That's the direction and the strength. We assume the relationship is linear when we are doing this. So how do we do it? We use a really simple statistic for this. It's called a Pearson's R. You may have heard about that if you've taken a stats class. Another word for that is a correlation coefficient. And I would normally have you guys run these on computers, but all you do is type in, does this variable correlate with this variable? And it's gonna pop out a number. And that number, or that coefficient, is going to range between -1 and +1. So it's always going to be between those 2 things. This is a list of generally what those correlation coefficients would indicate. If you got a -1, which is a perfect negative correlation, which is not going to happen, that never happens. That basically means you're looking at the same 2 variables, but that's a perfect negative correlation. As we get towards 0, the correlation gets weaker, okay, weaker, 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 -0.10, it's a weak negative correlation. If you get a correlation coefficient of 0, there's no relationship there, there's no correlation. So those 2 things don't really have a strong relationship at all. And then as the number goes past 0 and goes towards 1, you get a very, very strong positive correlation. Yes, as this number goes up, this other, as this variable goes up, this other variable really, really goes up. To be honest, where it says weak negative correlation around -0.1 and weak positive correlation about 0.10. Those are actually decent correlations. When you get up like past 0.5, those are really, really strong correlations. But you've probably heard people say a million times over, correlation does not imply causation, right? Just because one number or one variable goes up and another variable goes up, that doesn't mean that one is causing the other. This is a frequent phrase we hear a lot. Correlation does not imply causation. And it's true. There are really fun websites that you can go to called Spurious Correlations that can show you just how strongly two things can correlate, even though it's clear that one is not causing the other. So look at this graphic. This is the amount that the US spends on science, space, and technology each year, and it correlates with the number of suicides by hanging, strangulation, and suffocation. Look at that Pearson's R right there in the middle. It says it correlates at 0.99. That's as strong of a correlation as you're ever going to see. If you were science illiterate, you would look at that and say, wow, it looks like the amount that we spend on space technology is causing people to kill themselves. Clearly, that is not what's going on here. What would we need for this relationship? A lot of control variables, because that's probably not causing these deaths, right? These two things correlate strongly, but they're not causing each other. Let's look at another one. Per capita consumption of mozzarella cheese correlates with the number of civil engineering doctorates awarded. That correlates at 0.95. Wow. Do you guys actually think that the number of engineers that the United States produces every year is being caused by how much mozzarella cheese this country consumes? I don't think so, right? That's a really, really strong correlation. There's just no way that A is causing B. The number of people who drown by falling into a pool correlates with the number of films that Nicolas Cage appeared in. That correlates at 0.66. That's also, it's not 0.99, but that's a pretty strong correlation. Do we really think that people falling into a pool has a relationship with how many films Nicolas Cage participates in? Well, maybe. I don't know. I hate him. I think he's a terrible actor. I don't get it at all. So like maybe you could sell me on this one, but you guys get it, right? These things are not causing one another to happen. Okay. So